Hello, my name is Isabel Medlock. I am a fourth-year PhD student at Yale University working with DESI, and today I'm going to be talking about probing baryonic feedback and cosmological tensions with fast radio bursts, insights from the CAMELS project. To set the stage, right now we're at a really exciting time in cosmology and astrophysics with all these current and ongoing missions and planned missions, as well as advances in computational techniques and advances in simulations. We're really at a moment where we're poised to transform our understanding of cosmology and astrophysics. But one of the big uncertainties that has been identified in limiting our ability to fully harness these tools is the effects of baryons on the universe, which is quite poorly understood. Baryons have complex and wide-ranging effects on the physics of our universe. I'm interested in two scales specifically, that Milky Way-like systems and looking at the baryon cycle in the circumgalactic medium. As a reminder, the circumgalactic medium, or CGM, is roughly defined as the region beyond the galactic disk, but within the halo's virial radius. And this region is home and the interface to a lot of complex baryonic feedback processes, such as accretion, and then feedback from AGN and stars, recycling gas. And these processes all interact with each other and are quite complex and not well understood. But it's really important that we understand these because they really shape the formation and evolution of galaxies and clusters. And then on a larger scale, baryons have a complex effect on the large-scale structure of our universe, and this affects measurements of cosmological parameters, such as S8, for example. And in the case of S8, we know that there's this tension between late universe measurements, such as through weak lensing, and early universe measurements, such as through the CMB of S8, which could potentially be resolved if we fully understood the effects of baryons on the systematics of these measurements. One way we can look at the effects of baryons on the universe at all scales is through the matter-power spectrum. So this plot is showing the matter-power spectrum of a hydrodynamical simulation, which includes gas and baryons, and the ratio of that to the dark matter-only n-body simulation. And if baryons had no effects on the clustering and structure of matter in the universe, we would expect this ratio to just be a straight line at 1. But looking at this plot, that's clearly not the case. We see that baryonic effects actually suppress the matter-power spectrum at certain scales due to things like supernova and AGN feedback pushing matter out of halos. Then at very, very small scales, we see an enhancement in the matter-power spectrum because of things like cooling. But the actual effect on the matter-power spectrum varies significantly depending on which simulation you look at. So each of these lines are from different simulations, and as you can see, the differences are quite extreme. So what we really need to kind of disentangle this problem is a clean and straightforward observable. And what we're proposing to use is something called fast radio bursts. And fast radio bursts were recently discovered in 2007, relatively recently, and they're milliseconds long, extremely energetic pulses of radio waves that are coming from cosmological distances, extragalactic distances, usually outside of our galaxy. So again, first discovered in 2007. In 2013, the next 4 FRBs were discovered, and this term FRB was coined. And then now, in present day, 2025, thanks to facilities like CHIME, ASCAP, DSA, we have now detected thousands of FRBs and really expect to detect tens of thousands of FRBs per year in the future. And why are FRBs exciting? Aside from just being really cool phenomena in themselves, they're also really good cosmological probes, and that's because FRBs are direct tracers of ionized baryons and the intervening medium along their line of sight. So the key observable associated with an FRB is something called the dispersion measure, or DM. Throughout the talk, I'll use DM as a dispersion measure and not dark matter as it's commonly used. And DM is basically the integral of free electrons along the line of sight from the FRB source to us, the observers. And as FRBs are coming from cosmological distances, they're really probing a lot of structure, and they're sensitive to structure at all these different scales. So the DM we observe contains contributions from the FRB host galaxy, the IGM, including voids and filaments, the CGM of intervening halos along the line of sight, and then information about the Milky Way itself, both the CGM of the Milky Way and the Milky Way ISM. So when thinking about FRBs, we have an idea of what the contribution of each of these components are to the DM, the host, the cosmic component, which includes the intergalactic medium and intervening halos, and then what is from the Milky Way. But to really disentangle each of these components, we need to know where the FRB is. In other words, we need localized FRBs. We usually define a localized FRB as an FRB with known redshift in host galaxy. And although we have thousands of FRBs that have been detected now, we only have around 100 localized FRBs, which limits our ability to apply FRBs currently. But these facilities like CHIME and DSA are really focusing their aim on now detecting localized FRBs. So in the next few years, we expect to detect tens of thousands of localized FRBs with these new facilities and upgrades. And that means that really now is the time to make these theoretical investigations as to what we can do with these localized FRBs. I'm going to talk about, basically in this talk, how we can use these upcoming FRBs to constrain models of baryonic feedback on two scales, on the scale of the CGM and then on the scale of large-scale structure with cosmological implications. And these are the two papers I'm talking about. First, I want to introduce the CAMELS project, which is the data set we've used for these projects. The CAMELS project is now a set of over 14,000 simulations. 7,000 plus are state-of-the-art hydrodynamical simulations, 6,000 plus are n-body simulations, and it's primarily designed for machine learning applications. And within the hydro simulation suite of CAMELS, we have simulations run with currently 9 different codes or subgrid models, including IllustrisTNG, SIMBA, and Astrid, which I've worked on in my investigation. In addition to having these different hydro codes, within each hydro code, we have simulations with variations in cosmological and astrophysical parameters, and that's what leaves us with these thousands of simulations. And there's these different sets, including the one parameter set, which is what I will be using, where we vary one of these cosmological or astrophysical parameters at a time while holding the rest constant, and that really allows us to disentangle the effect of that parameter. And here with this video, I just want to quickly demonstrate how drastically these models can shape the evolution of baryons and gas in simulations. So these are 8 simulations in CAMELS of the fiducial subgrid models, all with the same initial conditions, box size and resolution, and so on. But as you can see, the evolution of the gas is drastically different, with simulations like SIMBA really blowing the baryons out of halos, whereas some like Astrid or IllustrisTNG are a bit more tame. So in my work, I've used the IllustrisTNG, SIMBA, and Astrid suites of the CAMELS project with the one parameter set and the 25 megaparsec box length iteration. And in these sets, we have varied 6 parameters, 2 cosmological parameters, omega matter and sigma 8, and then 4 astrophysical parameters, 2 that describe supernova feedback and 2 that describe AGN feedback. And for each of these 3 models, this table summarizes what each of those astrophysical parameters actually is controlling, but it's important to note that when comparing between models such as TNG and SIMBA, the same parameter can have quite different meaning because each model is implemented differently. So we start by looking at the dispersion measure of a single box, a single simulation box. This is at redshift 0.05, the fiducial model for SIMBA, TNG, and Astrid. And from these maps alone, we can see there's a significant difference in the distribution of baryonic matter. The SIMBA map appears to be more fuzzy, whereas TNG and Astrid, the filaments and halos are just tighter, more clumped together. And we can also see that difference in the histogram on the right, where we're just plotting the distribution of dispersion measures within each of these maps. And SIMBA has a slightly narrower distribution because overall the baryons in the box are more uniformly distributed, whereas Astrid has the widest distribution because sight lines will be passing through voids with a very low dispersion measure, and then other sight lines will be passing through very dense regions, leading to these higher dispersion measure sight lines, and that leads to more variance in the distribution of dispersion measure. And now, narrowing in on the halos themselves in these simulations, we have made plots of the radial profile of excess dispersion measure. And when we say excess, we mean excess in comparison to just the background dispersion measure of the box from the IGM. So here we're plotting from left to right SIMBA, TNG, and Astrid for 2 mass bins. And as we can see in these plots, SIMBA halos are the most evacuated baryons with the lowest DM excess because they have a stronger feedback model, whereas Astrid, which had the weaker feedback model, is the least evacuated with the largest DM excess. And we actually see DM excess out to a few factors of R200, which is kind of indicating that this boundary between the halo and the IGM, or the CGM and the IGM, is a bit nebulous. FRBs are usually actually found at cosmological distances, so we repeat the same exercise on integrated dispersion measure sight lines out to redshift of 1 for the same 3 fiducial models. And this plot really just highlights the difference even more strongly, that when we have this model like SIMBA, where feedback is stronger, baryons are more uniform, we're seeing this much narrower distribution dispersion measures compared to Astrid with this much wider distribution and dispersion measures. That was all for just a single redshift, but we can describe the redshift evolution of this distribution with something called the McQuart relation, which is plotted here, where redshift is on the x-axis and the dispersion measure is on the y-axis. And we can describe this analytically with this equation. That's the black line in the plot. And then there's a scatter around that line, which is described with this distribution. And we can simplify, we can parameterize this distribution with something called this F parameter. And this F parameter really tells us about the variance in the dispersion measure distribution at a single redshift, which reflects in turn the distribution of baryons, whether they're more uniformly distributed or are they more collapsed. So we measure this F parameter in CAMELS in the 1 parameter set of TNG, SIMBA, and Astrid for over 100 simulations. And this is plotted here. So there's 6 panels, 6 different parameters have been varied, and you can see how the F parameter changes depending on how we vary these parameters. So something quite straightforward, ASN2 is the strength of supernova feedback winds. As we increase the strength of supernova feedback winds, we expect baryons to be blown out more, and this F parameter to decrease because a lower F parameter indicates stronger feedback. So that's behaving as we expect. But then in other cases, such as ASN1, we're actually seeing that as we increase ASN1, the F parameter is also increasing. Initially, that seems a bit counterintuitive, but when we looked closer at the simulations, we saw that increasing ASN1 actually suppressed the growth of black holes, and that in turn dampened the AGN feedback and overall dampened total feedback. So these results have really demonstrated that the F parameter FRB observables are really powerful probes of the effect of baryonic feedback on the distribution of baryons around halos, and that's something we can quite easily quantify with FRB observables. And now thinking about larger scales, let's call back to the introduction. Baryons have this very strong effect on the matter power spectrum, and we don't really have a model for that fully describes this, but people have attempted to make one, and one such attempt was through this thing called the baryonic spread metric. The baryonic spread metric is defined basically as the distance in a simulation that a gas particle has moved from initialization to the final snapshot that you're looking at. And in this paper, Gebhardt et al. 2024, they found that this baryonic spread metric broadly captures the global impact of feedback on matter clustering over a range of feedback and galaxy formation models in the CAMELS project. And this was really great, but the main problem here is that the spread metric is not an observable. So we need an observable alternative, and that we propose to be FRBs. So this plot is showing the correlation between this baryonic spread metric and our measurements of the F parameter. And we see that there's a very tight correlation between these two parameters, independent of the 3 different subgrid models and the variations of astrophysical parameters within each one. So this really indicates to us that the F parameter and FRB observables in general could be a robust observational probe for something like the baryonic spread, or even more directly, the effect of baryons on the matter power spectrum. So this is a similar plot to the baryon spread metric plot, where we're plotting the ratio of the matter power spectrum from a hydrodynamical simulation with baryons versus that of the matching one of dark matter only n-body. And we can see that the degree of suppression due to the baryons in each of these simulations is quite well tracked by this F parameter. There's a clear correlation between this F parameter and the amount of suppression. So I think this really serves as a proof of concept that the F parameter and other FRB observables would be very strong probes to quantify the effect of baryons on the matter power spectrum, with applications to correcting systematics in weak lensing measurements of S8, for example. So this is in the early stages, so there's a lot of caveats and future work that still needs to be done. For instance, the CAMELS boxes that we use are the 25 megaparsec boxes, and these are too small to properly capture cosmic variance. And what this means for our measurements is that our F parameter values are systematically biased lower. But luckily, the CAMELS project has been working on larger boxes, so we're currently working right now on rerunning our analysis on larger boxes that do properly account for cosmic variance. That's the next step to the future hope of comparing 2 observations. We're also working on adding more subgrid models to our analysis, looking forward to comparing with future observations. And we are also thinking about going beyond the CAMELS project and looking at large simulation boxes like Millennium TNG and the Flamingo project. I'm just going to end with my conclusions and leave them here, but I think the main point I want to finish with is that FRBs are these very powerful and promising probes of cosmology and galaxy physics, and in the next few years we're expecting to have a large number of detections, so right now is really the time to do the modeling and simulations to prepare for those observations so we can fully harness the power that FRBs have in helping us understand cosmology and astrophysics better. Thank you.